Okay, let's talk about lesson 5. In lesson 4, we found a way to find limits or to evaluate limits by actually using derivatives. Well, lesson 5 is also about using derivatives to evaluate limits. Now, this particular method is named after a mathematician whose last name was L'Hopital. So this is going to be referred to as L'Hopital's rule. And if you have your handout, if you have your notes, I'm going to let you read through those. I'm not going to waste our airtime reading all of that to you. I just want to say this. This particular approach can be used when you evaluate a limit as x approaches some number and the limit turns out to be 0 over 0, or if it turns out to be infinity over infinity. So we like our shortcut rules and our rules for finding derivatives, and we're going to be able to use those when evaluating limits. So let's just go ahead and look at some examples. So the first example that we have is for us to evaluate the limit of 2x squared minus 9x minus 5 over x minus 5 as x approaches 5. Okay, so let me remind you that the first thing you ever want to do when you need to evaluate a limit is to substitute. Substitute 5 everywhere you have an x and see what you get, because oftentimes direct substitution will give you your answer. So let's see what happens. If I substitute 5 for x and square it, 9 times 5 minus 5, denominator, okay, that's looking pretty obvious that we're going to get a 0 in the denominator. 5 squared is 25. 25 times 2 is 50. So I have 50 minus 45 minus 5, and that is 0. So L'Hopital's rule is a viable tool to use to evaluate this limit. One of the things that we learned back in Unit 1 was that if you ended up with 0 over 0, the idea was to do more work and to rewrite this expression in a different form that you could then perhaps substitute 5 into and get your answer. Okay, and that still holds true for many cases. But here's what I want to show you. L'Hopital's rule says that if you will find the derivative of the numerator and the derivative of the denominator and find the limit as x, in this case, approaches 5 of each, then when we substitute, we very well may just get our answer. So let's go ahead and find the derivative of the numerator. Well, let me show it. So the limit as x approaches 5 of 2x squared minus 9x minus 5. The limit of x minus 5 as x approaches 5. So the limit as x approaches 5, find the derivative, which is 4x minus 9. Divide that by the limit as x approaches the derivative of x is 1. Derivative of minus 5 or negative 5 is 0. So let's see. Can we substitute? Substituting 5 in for x, we get 4 times, am I off the page? No. Okay, so 4 times 5 minus 9 over, what's the limit of 1 as x approaches 5? It is 1. And so therefore, 4 times 5 is 20. 20 minus 9 is 11. So here's another way that derivatives can be used to evaluate a limit. And so this is useful when you have a rational function like we have here. to find the derivative of the numerator, find the derivative of the denominator, and then substitute. Okay? Okay, so that was our first example. Let's move on to our next example. The next example that we have, and by the way, just out of curiosity, what would you do with this expression if you wanted to do more work on this expression to rewrite it in a different form and not use L'Hopital's rule? It's your favorite thing. You would factor the numerator. The denominator's already factored. You would see if a factor would cancel and then substitute. Okay, so now let's go to our next example. Our next example, we have the limit of the square root of 4 minus x minus 3 over x plus 5 as x approaches negative 5. Well, by first glancing, I notice that negative 5 is going to make the denominator 0. So I'm going to make sure that I'm going to see what happens with the numerator if I substitute negative 5. 4 minus the negative 5 would give us the square root of 9, which is 3, and 3 minus 3 is 0. So we do get 0 over 0. So L'Hopital's rule can be used on this example. So what does L'Hopital's rule say? L'Hopital's rule says, okay, find the derivative of the numerator. Well, if you think about this 4 minus x being to the 1/2 power, then the let me put my x's approaching negative 5. The derivative of the square root of 4 minus x will be 1/2 4 minus x to the negative 1/2 times the derivative of the inside, which is negative 1. And all of that will be over the limit as x approaches negative 5 of 1, the derivative of the denominator. Okay, so it looks like I'm in good shape because the limit of this denominator, the limit of the denominator here, let me draw my big bar, is going to be 1. Now let's see if we can substitute negative 5 for x. Well, what is 4 minus negative 5? That would be 1/2. So I'm looking at 1/2 times 9 to the negative 1/2 times negative 1. Okay, I can ignore that denominator. Now, if I want to evaluate 9 to the negative 1/2, I can take 9 to the negative 1/2 and write it as 1 over 9 to the 1/2 power, and then multiply that by the negative 1. What is 9 to the 1/2? That'd be 3. So I'm looking at 1/2 times 1/3 times negative 1, and that value is negative 1/6. And I'm pretty sure, yep, I left off, when you're looking at the notes that I've provided in the completed form, I'm realizing that I left this piece off. So your answer on the notes that I've provided should be negative 1/6 because I forgot to do the derivative of the inside piece. I left this piece off. Okay? All right, then moving on to the next example. Our next example, all right, flipping to the back. The next example is going to be an example where we get to use L'Hopital's rule multiple times. So my example here is the limit of 2x. No, it's not. I lied. Sorry. It's the limit of x squared over e to the negative x as x approaches negative infinity. Okay, well, if you substitute negative infinity in the numerator, if you think about what's going on as x approaches negative infinity, you're going to ultimately end up with infinity in the numerator and also infinity in the denominator. So infinity over infinity, L'Hopital's rule is an option. So L'Hopital's rule says find the limit of the find the derivative of x squared. So that's the 2x, the limit of 2x as x approaches negative infinity, over, I'll do the same thing with the denominator, the limit as x approaches negative infinity of e to the negative x. Okay, well, let's think about 2 times this, quote, negative infinity. That's still going to be infinity on the top. This is still going to be infinity on the bottom. Well, because we still end up with infinity over infinity, we can use L'Hopital's rule again. You can use L'Hopital's rule enough times until you finally understand and know what the derivative is. Okay, so derivative, or the limit of the derivative of the numerator is 2. That makes me feel good. As x approaches negative infinity, the derivative of e to the negative x is negative e to the negative x power. So now let's think about this. My numerator is 2. Let's talk about the denominator for a second. Hang on just a minute. Did I do that right? Yes. Okay, I thought I had one too many things going on in there. Okay, so here I have, oh, I know what I did. Okay, so I took the derivative of the numerator. This is not the derivative of e to the negative x. This derivative should be negative. That's not going to change this at all. But now when I find the derivative of this expression, I should end up with positive e to the negative x. Okay, so now e to the negative x, when x approaches negative infinity, is going to give us something really, really big. Infinity is not a number at all, but infinity describes what's happening to the denominator. And since your numerator will always be 2, your denominator gets bigger and bigger and bigger. So therefore, the limit of this expression is equal to 0. Because 2 over something really, really big makes the whole fraction equal 0. Okay? All right. That one you just might have to think about and look at a little bit longer, but you can do that one. You can do it. All right, so let's do the next one. My next one, the nice thing is that the next example is simply a polynomial over a polynomial. And I want to find the limit as x approaches -2 of x cubed plus x squared minus 8x minus 12 over x cubed plus 8x squared plus 20x plus 16. Okay, so if you will take my word for it, when we substitute -2 here, 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 and here, we're going to end up with 0 over 0. All right, so let's go about taking the derivative of the numerator. So the limit as x approaches -2 of 3x squared plus 2x minus 8 over, actually that should be over, the limit as x approaches negative 2 of 3x squared plus 16x plus 20. If I substitute if I substitute negative 2 here, I'm going to get a 12 minus 4 minus 8. And negative 2 times, okay, so in my denominator, I get 12 minus 32 plus 20. And that's still 0 over 0. So I want to use L'Hopital's rule again. So the limit as x approaches negative 2, I want to do this enough times until when I substitute negative 2, I get a value. So the derivative of the numerator is 6x plus 2. The derivative of the denominator is 6x plus 16 as x approaches negative 2. Now let's see if we can substitute negative 2. Okay, so we have 6 times negative 2 plus 2 over 6 times negative 2 plus 16, and I'm feeling really good about this. So this is negative 12 plus 2 is negative 10, and negative 12 plus 16 is 4. So there's your limit in reduced form. That would be negative 5 over 2. So this was a scenario where you had a limit in which direct substitution yielded 0 over 0. Okay? In Unit 1, we would have said do more work. Well, what would the work be on this expression to write it in a different form? Well, that's the question. I'm not coming up with anything right now myself. So that's where L'Hopital's rule is really, really nice. Okay, the next example involves trig functions. So let's talk about what we can do with those. So the limit, we have the limit of sine of x times 1 minus cosine of x over x squared as x approaches 0. Okay, well, if we think about substituting 0, I have sine of 0 times 1 minus cosine of 0 over 0 squared. Well, what is sine of 0? Okay, the ordered pair at 0 is 1, 0. Sine is 0, so that's 0. It doesn't really even matter what that is. We end up with 0 over 0. Okay, so let's talk about what we can do with this particular example. So what if I were to actually separate this? I can rewrite this as the limit as x approaches 0 of sine of x over x times the limit as x approaches 0 of 1 minus cosine of x over x. So if you look at this, if I were to multiply sine of x over x by 1 minus cosine over x, I would get this back again. And this is perfectly legal. All right, so I'm going to use L'Hopital's rule on each piece. Okay, so if I look at the limit as x approaches 0, the derivative of sine is cosine, and the derivative of x is 1. Okay, I'll come back to that in just a minute. Now let's talk about the derivative of this piece. Okay, so the limit of x as x approaches 0. Find the derivative of the numerator. Derivative of 1 is 0. Now the derivative of cosine is negative sign, but the negative sign out front is going to make that sine of x over the limit as x approaches 0. The derivative of this x is 1. So I can actually just ignore those. Now let's do a little substitution. What is cosine of 0? We'll multiply that by the sine of 0. And our circle, 1, 0. What's cosine of 0? 1. And what is the sine of 0? 0. So the limit of this expression is equal to 1. And we did that by rewriting the expression and then using L'Hopital's rule. Okay, so remember, L'Hopital's rule only can be used when direct substitution gives you 0 over 0 or infinity over infinity. Okay, the next example is a polynomial function, so I'm going to skip over that one. And I will move down to, I believe, the last one. The last example is the limit of 4x squared minus 3x plus 2 over e to the 2x plus the natural log of x as x approaches, oops, that's an arrow, infinity. Okay, so let's just think about something. Since x is approaching infinity, I think it's safe to say that as x gets bigger and bigger for this term is going to get bigger and bigger and bigger. This term is going to get bigger but negative, but it's still not going to be as big as this. And then you add 2. So the numerator is infinity. All right, e to the 2x, as x gets bigger and bigger and bigger, the power gets bigger and bigger and bigger, which means this expression gets bigger and bigger and bigger. And then the natural log of x, it gets bigger as well as x gets bigger. So we have a scenario where we have infinity over infinity. Okay? All right, so let's approach this from a L'Hopital's rule. Let's find the limit of 4 x squared minus 3x plus 2 as x approaches infinity, and divide that by the limit as x approaches infinity of e to the 2x plus the natural log of x. All right, so let's do the derivative here. So the derivative is, numerator is 8x minus 3, and that's, I have the limit as x approaches infinity, over the derivative of e to the 2x is 2e to the 2x. The derivative of natural log of x is 1 over x. Okay, if I do the same thing I did earlier as plug bigger and bigger numbers in for x, my numerator does get bigger. But let's talk about this denominator. If I put bigger and bigger numbers in for x here, the power gets bigger and bigger, and then therefore this whole term gets bigger. Well, even with respect to plugging in bigger and bigger numbers of x here, you're adding a fraction. So really, this is somewhat insignificant to the value of the denominator. Bottom line is this. The numerator, as x approaches infinity, is getting big, but the denominator, as x approaches infinity, is getting bigger faster. Well, when the denominator gets bigger faster, that means the whole fraction is equal to 0. So the limit of this expression as x approaches infinity is 0. And we did that using L'Hopital's rule. So you now have a couple of different ways and a couple of different tools to use to evaluate limits, and both of them involve using derivatives.